What if the pyramids of Giza were built using mathematical techniques so advanced that modern engineers still struggle to replicate them? What if ancient Egyptian mathematics held secrets that would revolutionize our understanding of construction, astronomy, and even the foundations of modern engineering? I'm the sleepy computer scientist, and today we're diving deep into the shocking world of ancient Egyptian mathematics. Buckle up, because what you're about to discover will change everything you thought you knew about ancient civilizations. When you think of ancient Egypt, you probably picture pharaohs, mummies, and massive pyramids rising from the desert sand. But behind every one of those architectural marvels was something far more powerful than brute force. It was mathematics, pure, elegant, and shockingly sophisticated mathematics. The ancient Egyptians didn't just stumble upon ways to build the pyramids. They developed an entire mathematical system that allowed them to calculate areas, volumes, slopes, and angles with stunning precision. And here's the kicker. They did it all without our modern number system, without calculators, and without the mathematical notation we take for granted today. Let me paint you a picture. It's 2600 BCE. You're standing in the desert, and someone asks you to build a structure so precise that its base is level to within just 2 centimeters across a span of 230 meters. Oh, and by the way, you need to align it almost perfectly with true north, achieving an accuracy of just 3/60ths of a single degree. Sounds impossible, right? Well, the ancient Egyptians did exactly that when they built the Great Pyramid of Khufu, and they didn't do it through trial and error or dumb luck. They did it through mathematics. The risk here isn't just about losing appreciation for ancient achievements. It's about losing understanding of foundational techniques that still influence how we approach engineering problems today. When we dismiss ancient Egyptian mathematics as primitive or simplistic, we're actually cutting ourselves off from insights that could enhance our modern methods. These weren't simple builders stacking stones. These were sophisticated mathematicians who understood principles that wouldn't be formally described in Europe for thousands of years. Now here's where things get really interesting. The ancient Egyptians used a mathematical system based entirely on unit fractions. Well, instead of writing fractions like we do, with any number in the numerator, they almost exclusively used fractions with 1 in the numerator. So instead of writing 2/3, they would write 1/2 plus 1/6. Instead of 3/4, they'd write 1/2 plus 1/4. This might sound limiting, but it was actually incredibly powerful. It forced Egyptian mathematicians to think about numbers in a fundamentally different way, and this alternative perspective led to some remarkable insights. The Rhind mathematical papyrus, one of our best sources for understanding Egyptian mathematics, dates back to around 1650 BCE. It's basically an ancient textbook, and let me tell you, it's mind-blowing. This document contains 84 mathematical problems covering everything from basic arithmetic to complex geometric calculations. It shows us how the Egyptians calculated areas of circles, volumes of cylindrical granaries, and slopes of pyramids. But more than that, it reveals a mathematical philosophy that's completely different from our own. Let's talk about one specific example that'll blow your mind. They would take the diameter, subtract 1/9 of it, and then square the result. Let me break that down. If you have a circle with a diameter of 9 units, you'd subtract 1 unit, giving you 8. Then you'd square 8 to get 64. According to this method, a circle with a diameter of 9 has an area of 64 square units. Now, how accurate is this? Well, using our modern formula with pi, the actual area would be about 63.617 square units. The Egyptian method gives us an implied value for pi of about 3.1605. Compare that to the actual value of pi, which is 3.14159, and you'll see they were off by less than 1%. This is absolutely remarkable for a civilization that existed more than 3,500 years ago. But how did they come up with this method? That's the question that has puzzled historians and mathematicians for decades. The papyri don't show us the derivation, just the method itself. This suggests that Egyptian mathematics was highly practical and empirically driven. They weren't necessarily concerned with abstract proofs the way Greek mathematicians would be centuries later. Instead, they focused on methods that worked, methods that could be applied reliably to solve real-world problems. And this practical approach is exactly what made their mathematics so powerful for engineering and construction. Now let's talk about another shocking secret of Egyptian mathematics: their understanding of geometry. The Egyptians didn't just know how to calculate areas and volumes. They understood geometric relationships in ways that allowed them to solve incredibly complex construction problems. Take the sect, for example. This was the Egyptian unit for measuring the slope of a pyramid. The sect told you how many palms the pyramid would run horizontally for every cubit it rose vertically. It's essentially the ancient Egyptian version of our modern slope or gradient. Why is this important? Because building a pyramid requires absolute consistency in slope. If you're building a structure that's going to be 146 meters tall, even a tiny error in slope at the bottom will result in massive errors at the top. The four sides won't meet properly at the apex, and the whole structure could become unstable. The Egyptians used the sect system to ensure that every stone was placed at exactly the right angle, maintaining perfect geometric precision throughout the entire construction process. This level of mathematical sophistication is staggering when you consider they were working without modern surveying equipment, without theodolites, without laser levels. But here's something even more shocking. Recent analysis of the pyramids has revealed that the Egyptians may have understood the golden ratio, that famous mathematical constant approximately equal to 1.618, which shows up throughout nature and art. The ratio of the slant height to half the base of the Great Pyramid is remarkably close to the golden ratio. Now, scholars debate whether this was intentional or coincidental, but given everything else we know about Egyptian mathematical sophistication, it's entirely plausible that they deliberately incorporated this ratio into their designs. Let's shift gears and talk about Egyptian astronomy, because this is where their mathematical abilities really shine. The ancient Egyptians were master astronomers. They needed to be. Their entire civilization depended on the annual flooding of the Nile River, which brought nutrient-rich silt to fertilize their crops. Predicting when this flood would occur required careful astronomical observation and mathematical calculation. The Egyptians developed a calendar with 365 days, divided into 12 months of 30 days each, plus 5 additional days. This calendar was based on their observations of the star Sirius, whose heliacal rising, that is, its first appearance in the dawn sky after a period of invisibility, coincided with the Nile flood. But tracking stellar and solar movements requires mathematics. You need to be able to measure angles, track positions over time, and make predictions based on observed patterns. The Egyptians developed sophisticated methods for doing all of this. They created star clocks, astronomical instruments that allowed them to tell time at night by observing the positions of specific stars. They divided the night into 12 hours, though these were variable hours that changed length with the seasons. The mathematical calculations required to create and use these star clocks demonstrate a deep understanding of spherical geometry and celestial mechanics. Now here's a revelation that'll really get you thinking. The Egyptians understood the concept of algebraic equations, even though they didn't have our modern algebraic notation. In the Rhind Papyrus, we find problems that are essentially linear equations. For example, one problem asks to find a quantity such that when it's added to its seventh, the result equals 19. In modern notation, we'd write this as x plus x divided by 7 equals 19. The Egyptians solved this using a method called false position. They'd guess an answer, see how far off they were, and then scale their guess proportionally to get the correct answer. This method works because of the linear relationship between the variable and the result. Let me walk you through a specific example to show you how clever this technique is. Suppose we want to solve that equation I just mentioned. An Egyptian scribe might start by guessing that the answer is 7 because 7 is convenient when you're dividing by 7. If x equals 7, then x plus x divided by 7 equals 7 plus 1 equals 8. But we want 19, not 8. So we're off by a factor of 19 divided by 8. Therefore, the actual answer must be 7 times 19 divided by 8, which equals 16.625. And indeed, if you check, 16.625 plus 16.625 divided by 7 equals 19, exactly. The Egyptians would have expressed this answer using their unit fraction system, but the method is absolutely sound mathematically. This false position method might seem primitive compared to our modern algebraic techniques, but think about what it represents. It shows that the Egyptians understood proportionality, linear relationships, and systematic problem-solving strategies. These are fundamental algebraic concepts, even if the notation looks completely different from what we use today. And here's the thing, this method was being used in Egypt, while most of the rest of the world was still figuring out basic arithmetic. Let's talk about another shocking aspect of Egyptian mathematics, their multiplication and division techniques. The Egyptians used a method based on doubling and halving, which is fundamentally different from the multiplication algorithms we learn in school. To multiply two numbers, they would repeatedly double one number while halving the other, then add up the appropriate values. This might sound complicated, but it's actually beautifully elegant and efficient. Here's how it works. Suppose you want to multiply 13 by 9. You'd set up two columns. In the first column, you'd start with 9, and keep doubling 9, 18, 36, 72. In the second column, you'd start with 1, and also keep doubling 1, 2, 4, 8. Now here's the clever part. You need to figure out which powers of 2 add up to 13. That's 8 plus 4 plus 1. So you take the corresponding values from the first column, 72 plus 36 plus 9 equals 117. And indeed, 13 times 9 equals 117. The Egyptians could multiply any two numbers using just doubling and addition. No memorizing multiplication tables required. Why is this significant? Because this method actually has a lot in common with how modern computers multiply numbers. Digital computers use binary arithmetic, and the Egyptian doubling method is essentially a way of breaking numbers down into binary components. The ancient Egyptians stumbled upon a technique that would become fundamental to computing technology thousands of years later. Now that's what I call being ahead of your time. Division works similarly, but in reverse. To divide a number, you'd use the same doubling process, but you'd be looking for which doubled values add up to the dividend. The Egyptians became incredibly proficient at these techniques, and scribes were trained extensively in these methods. Being a scribe in ancient Egypt was a prestigious profession precisely because it required mastery of these mathematical skills. The calculations needed for administration, tax collection, construction projects, and trade all depended on having people who could perform these operations accurately and efficiently. Now, let's address something that might be puzzling you. If the Egyptians were so mathematically sophisticated, why don't we see more abstract mathematical theorems from ancient Egypt? Why don't we have Egyptian equivalents of Euclid's Elements or Pythagoras' theorem? The answer lies in the purpose and philosophy of Egyptian mathematics. Egyptian mathematics was fundamentally practical and empirical. It was designed to solve specific concrete problems. How much grain do we need to feed the workers building this pyramid? What angle should we cut these stones? When will the Nile flood? Egyptian mathematicians weren't particularly interested in abstract proofs or generalizations. They wanted methods that worked reliably for the problems they faced. This doesn't make Egyptian mathematics less sophisticated. It makes it differently sophisticated. It's the difference between applied mathematics and pure mathematics, between engineering and theoretical physics. Both are valuable, both require deep insight, but they approach problems from different angles. The Egyptians developed the mathematical tools they needed for their civilization to flourish, and those tools were remarkably effective. Consider the Moscow Mathematical Papyrus, another crucial document for understanding Egyptian mathematics. This papyrus, dating to around 1900 BCE, contains 25 problems, and one of them is particularly stunning. Problem 14 asks for the volume of a truncated pyramid, also called a frustum. This is the shape you get when you cut the top off a pyramid with a plane parallel to the base. The formula given in the papyrus is exactly correct. Volume equals height times the quantity A squared plus A times B plus B squared divided by 3, where h is the height, h is the side length of the base, and b is the side length of the top. Now think about this for a moment. This formula is not obvious. Deriving it requires understanding of three-dimensional geometry and the ability to break complex shapes into simpler components. The fact that the Egyptians had this formula more than 3,900 years ago is absolutely remarkable. This wasn't just practical knowledge for construction, this represents a deep geometric understanding that wouldn't be matched in Europe for millennia. When you see formulas like this in Egyptian papyri, you realize that we're not talking about primitive mathematics. We're talking about a sophisticated mathematical tradition that solved problems we still consider challenging today. Let's talk about how the Egyptians actually performed their astronomical calculations, because this is where mathematics and observation come together in fascinating ways. The Egyptians noticed that certain stars, which they called decans, would rise heliacally at intervals of about 10 days throughout the year. By tracking these decanal stars, they could mark the passage of time and create calendars. But here's what's mathematically interesting. They divided the night sky into 36 decans, corresponding to the 36 weeks of their 360-day year, plus those 5 extra days. This system required careful angular measurements and record keeping over long periods. The Egyptians had to track which stars were visible, at which times of year, measure their positions relative to the horizon, and create tables that would allow them to tell time at night. The mathematics involved includes angular measurement, trigonometric relationships, although they wouldn't have called them that, and pattern recognition. They also had to account for the precession of the equinoxes, although they probably didn't understand the underlying cause. Over long periods, the positions of stars shift relative to the calendar, and the Egyptians would have noticed these gradual changes and incorporated them into their observations. The Temple of Karnak provides stunning evidence of Egyptian astronomical and mathematical sophistication. The main temple is aligned with the winter solstice sunrise, meaning that on that specific day, sunlight penetrates deep into the temple, illuminating the inner sanctuary. Achieving this alignment requires precise astronomical observations and careful mathematical calculation. You need to know the exact angle of the sunrise on the solstice, and you need to orient your entire massive temple structure accordingly. The fact that this alignment still works today, more than 3,000 years later, testifies to the accuracy of Egyptian mathematics and engineering. But let's dig even deeper. How did the Egyptians measure angles? They didn't have protractors or compasses in the modern sense. Instead, they used tools like the merkit, which was essentially a plumb line combined with a sighting tool. By aligning the merkit with stars and using careful observation, they could measure angles with impressive precision. They also used shadow clocks and sundials, which required understanding the mathematical relationships between the sun's position, the time of day, and the length and direction of shadows. All of this involves trigonometry, even if the Egyptians didn't formalize it the way later Greek and Indian mathematicians would. The construction of the pyramids themselves provides endless examples of mathematical sophistication. Consider just the problem of quarrying and transporting the stones. The Great Pyramid contains approximately 2.3 million stone blocks, each weighing an average of 2.5 tons. Some blocks weigh much more, up to 80 tons. Just organizing the logistics of such a project requires extensive mathematical calculation. How many workers do you need? How much food and water must you supply? How long will the project take? What's the most efficient way to transport stones from the quarry to the construction site? Every one of these questions requires mathematics to answer. The Egyptians had to calculate workforce requirements, material needs, and timeframes. They had to ensure that stone cutters, transporters, and builders were all working in coordination. This required sophisticated project management, which in turn required mathematics. Recent scholarship suggests that the pyramids were built during the Nile flood season, when farmers were unable to work their fields and were available for construction projects. This means the Egyptians had to calculate how much work could be done during each building season and plan the project accordingly. Multi-generational project planning on this scale represents an impressive application of mathematical thinking to practical problems. Now here's something that will really make you think differently about ancient Egypt. The layout of Egyptian cities and temples often incorporated mathematical ratios and geometric principles. The Egyptians used a measurement system based on the cubit, which was approximately 52.5 centimeters, the length from elbow to fingertips. They subdivided the cubit into smaller units, palms, fingers, and digits. This hierarchical measurement system allowed for precise specifications at multiple scales, from massive monuments down to fine artwork. But more interestingly, the proportions used in Egyptian art and architecture often follow mathematical patterns. The human figure in Egyptian art is typically divided into 18 squares from the sole of the foot to the hairline, with specific body parts occupying specific squares. This grid system is fundamentally mathematical, representing an understanding of proportion and scale. It allowed Egyptian artists to maintain consistent proportions across different sizes and contexts, whether they were creating a small statue or a colossal monument. This is applied geometry in service of art. Let's talk about the Egyptian understanding of right angles and perpendicular lines, because this is crucial for construction. To ensure that pyramid bases were perfectly square and that walls were perfectly vertical, the Egyptians needed reliable methods for creating right angles. One technique they used was the 3-4-5 triangle. If you create a triangle with sides of 3, 4, and 5 units, you automatically get a right angle between the 3-unit and 4-unit sides. This is a special case of the Pythagorean theorem, which states that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. Now, the Pythagorean theorem is named after the Greek mathematician Pythagoras, who lived around 500 BCE. But the 3-4-5 triangle was being used in Egypt at least 1,000 years before Pythagoras was born. There's evidence that Babylonians and Indians also knew about this relationship before the Greeks. So while Pythagoras may have been the first to prove the theorem in a general form, the practical knowledge existed much earlier. The Egyptians understood that certain triangles had this special property, and they used it extensively in construction to create precise right angles. The Egyptians also understood the concept of similarity in geometry. Similar shapes have the same proportions but different sizes. This concept is essential for scaling. If you have a small architectural model and you want to build a full-size version, you need to understand similarity to scale everything proportionally. The Egyptians clearly grasped this, as evidenced by the way they could create small-scale plans and then execute them at monumental scale while maintaining perfect proportions. This kind of scaling requires mathematical sophistication, particularly when working with the three-dimensional forms of pyramids and temples. Let me tell you about another mind-blowing aspect of Egyptian mathematics. Their ability to approximate. They understood that sometimes exact answers weren't necessary or practical, and they developed methods for finding good approximations efficiently. Their formula for the area of a circle that we discussed earlier is a perfect example. It's not exact, but it's close enough for practical purposes, and it's much simpler to calculate than a formula involving pi would be. This pragmatic approach to approximation is very modern in spirit. In engineering and applied mathematics today, we frequently use approximations because they're faster to compute and sufficient for the accuracy we need. The Egyptians also developed methods for approximating the areas of irregular shapes. They would break complex shapes into simpler components like triangles and rectangles, calculate the areas of these components and add them up. This is essentially the same strategy used in modern calculus, where we approximate areas under curves by breaking them into tiny rectangles. The Egyptians didn't have calculus, but they understood the fundamental principle: complex problems can be solved by breaking them down into simpler pieces. Now let's discuss the social and educational context of Egyptian mathematics. Mathematics wasn't universal knowledge in ancient Egypt. It was specialized knowledge possessed by scribes, who formed an educated elite. Boys from certain families would be sent to scribal schools where they would spend years learning reading, writing, and mathematics. The training was rigorous and demanding. Students would copy mathematical problems repeatedly, learning the standard methods for solving different types of problems. This educational system produced highly skilled calculators who could handle the mathematical needs of the state and temple administrations. The status of scribes in Egyptian society tells us something important about how mathematics was valued. Scribes could rise to high positions in the government. They were exempt from manual labor and taxation. They were respected and well compensated. This social status reflects the recognition that mathematical skills were valuable and difficult to acquire. In a society that produced such incredible architectural and engineering achievements, the people who could do the calculations enabling those achievements were naturally held in high regard. Here's something fascinating. Egyptian mathematical education wasn't just about memorizing formulas. Students learned problem-solving strategies that they could apply to new situations. The mathematical papyri that survive are essentially textbooks, showing worked examples of different problem types. But they also show variations on problems, encouraging students to adapt their methods. This pedagogical approach, learning through examples and variations, is remarkably similar to how mathematics is often taught today. It recognizes that mathematical understanding comes from practice and from seeing how methods apply across different contexts. Let's return to construction for a moment, because there's a specific technique the Egyptians used that demonstrates incredible mathematical insight. When building pyramids, they needed to ensure that the base was level, but leveling a platform of several hectares with an accuracy of a few centimeters is extraordinarily difficult. How did they do it? Evidence suggests they used water. They would create a network of small channels around the construction site, fill them with water, and use the water surface as a level reference. Water naturally finds its own level, so the water surface provides a perfectly level plane that can be used as a reference for all measurements. But here's the mathematical sophistication. Using water levels effectively requires understanding fluid mechanics and geometric relationships. You need to establish reference points at the same height as the water surface throughout your construction area. You need to account for the fact that water height might vary slightly due to atmospheric pressure changes. The Egyptians figured out how to use this natural leveling tool effectively over large areas, achieving remarkable precision. This represents an integration of physical understanding and mathematical method that's truly impressive. The orientation of the pyramids provides another stunning example of Egyptian mathematical and astronomical abilities. The Great Pyramid is aligned almost perfectly with true north. Its orientation is off by less than 1/10 of 1 degree. How did the Egyptians achieve this? They didn't have magnetic compasses which point to magnetic north, not true north anyway. Instead, they used the stars. By observing the rising and setting positions of stars, or by tracking the rotation of circumpolar stars around the celestial North Pole, they could determine true north with extraordinary accuracy. This required careful angular measurements and mathematical calculations to account for their observation point and the time of year. One proposed method involves observing a single star as it rises and sets, marking the exact spots on the horizon where these events occur, and then bisecting the angle between these 2 points. The midpoint of this bisection points to true north. This method requires precision in marking positions, measuring angles, and performing the bisection accurately. Another proposed method involves tracking circumpolar stars, those that never set below the horizon, and finding the point around which they appear to rotate. Either method demands both observational skill and mathematical sophistication. The fact that the pyramids are oriented so accurately tells us that whatever method the Egyptians used, they executed it with remarkable precision. Think about what this means for a moment. We're talking about people who lived more than 4,000 years ago, without any modern instruments, achieving orientations that we would struggle to match without our technology. They did this through careful observation, mathematical calculation, and probably generations of accumulated knowledge. This is not primitive. This is sophisticated science and mathematics applied with incredible skill. Now let's discuss how Egyptian mathematics influenced later civilizations. When the Greeks began developing their mathematical tradition, they were influenced by Egyptian knowledge. Greek scholars like Thales and Pythagoras are said to have traveled to Egypt to study. The geometric knowledge that would later be systematized in Euclid's Elements had roots in Egyptian practical geometry. The Greeks took this practical knowledge and transformed it into something more abstract and theoretical, focusing on proofs and generalizations. But the foundation came from the applied mathematics of civilizations like Egypt. Similarly, the Romans, who were master engineers and builders, inherited mathematical knowledge that ultimately traced back through the Greeks to sources including Egypt. The mathematical techniques used to build Roman aqueducts, roads, and buildings relied on geometric and arithmetic methods that had been developed and refined over thousands of years, with Egyptian mathematics being a crucial part of that tradition. Mathematical knowledge is cumulative. Each generation builds on what came before, and Egyptian mathematics was a fundamental building block in the structure of mathematical knowledge that we have today. But the influence extends beyond just mathematical content. The Egyptian approach to mathematics, practical problem-focused, empirically tested, represents one of the fundamental ways humans do mathematics. Not everyone needs to be a pure mathematician deriving abstract theorems. We also need applied mathematicians and engineers who can take mathematical tools and use them to solve real-world problems. The ancient Egyptians were master practitioners of applied mathematics, and their approach remains relevant today. In fact, in our modern world where computation and simulation are so important, the Egyptian emphasis on methods that work effectively has more resonance than ever. Let's talk about what we can learn from Egyptian mathematics today. First, it reminds us that mathematical sophistication can take many forms. The Egyptians didn't use the same notation or methods we use, but their mathematics was no less valid or powerful. This is important in our interconnected world, where different cultures have developed different mathematical traditions. We should recognize that there are multiple ways to approach mathematical problems, and we can learn from different traditions. Second, Egyptian mathematics shows us the power of practical applied mathematics. Sometimes we get caught up in abstract theory and forget that mathematics is fundamentally a tool for understanding and manipulating the world. The Egyptians never forgot this. Every mathematical method they developed had a purpose, whether it was building structures, managing grain supplies, or tracking the stars. This purposefulness is something modern mathematics education could benefit from. Students often ask when they'll ever use what they're learning. The Egyptians would never have had to ask that question. Third, the longevity and stability of Egyptian civilization, lasting roughly 3,000 years, was built in part on their mathematical achievements. Reliable calendars, effective administration, impressive architecture, these things required mathematics, and they contributed to the success and endurance of Egyptian civilization. This reminds us that mathematical literacy and capability have real consequences for society. Civilizations that develop strong mathematical traditions tend to flourish, those that neglect mathematics tend to struggle. Now here's a revelation that brings everything together. Modern engineering analysis of the pyramids has revealed something stunning. Using computer modeling and structural analysis, engineers have determined that the pyramids are almost perfectly designed for stability. The angle of the sides, typically between 51 and 54 degrees, represents an optimal balance between height and structural integrity. Make the angle steeper, and you risk collapse as the internal stresses become too great. Make it shallower, and you're using much more material than necessary for a given height. The Egyptians somehow figured out this optimal range, presumably through experience and mathematical analysis of successful and unsuccessful structures. This is engineering optimization, finding the best solution within given constraints. It's a sophisticated concept that requires mathematical modeling and analysis. Modern engineers use calculus, computer simulations, and finite element analysis to optimize designs. The Egyptians achieved similar results using their own methods, probably involving scaled models, empirical testing, and accumulated knowledge from previous projects. The fact that their results match what modern analysis tells us is optimal shows that their mathematical approach, however different from ours, was fundamentally sound. Consider also the internal structure of the pyramids. The Great Pyramid contains passages, chambers, and ventilation shafts, all carefully integrated into the overall structure. Designing this internal architecture, while maintaining structural integrity, requires three-dimensional geometric understanding and careful calculation of loads and stresses. The Grand Gallery, an ascending passage with a corbelled ceiling that rises 8.6 meters high, is a masterpiece of engineering. Each layer of the corbelling projects slightly inward, gradually closing the space until the sides meet at the top. This technique distributes weight effectively while creating a functional space. Designing such a structure requires understanding of both geometry and mechanics, both of which are fundamentally mathematical disciplines. Let's talk about some specific problems from the Rhind Papyrus to give you a better feel for Egyptian mathematical thinking. Problem 48 asks to compare the areas of a circle and a circumscribed square. The scribe calculates that a circle with diameter 9 has an area of 64, while the square has an area of 81. Therefore, the circle has an area that is 64/81 of the square's area. This kind of problem shows that Egyptians were thinking about mathematical relationships, not just calculating individual answers. They wanted to understand how different shapes compared to each other. Problem 79 asks about a problem involving loaves of bread and beer, comparing different distribution schemes. These problems show mathematics being applied to economic questions, essentially early operations research. The Egyptians understood that mathematics could help them make better decisions about resource allocation and distribution. This is the kind of applied mathematics that businesses and governments still use today, just with more sophisticated methods. Problem 50 asks to find the area of a circular field with diameter 9. This is straightforward application of their circular area formula. But the interesting thing is that the papyrus contains many such problems, variations on the same themes. This tells us that Egyptian mathematical education emphasized practice and mastery through repetition and variation. Students would work through many similar problems, internalizing the methods until they could apply them automatically. This pedagogical approach is time-tested and still used in mathematics education today. Here's another mind-blowing fact. The Egyptians understood the concept of mathematical proofs, even if their approach was different from the Greek style. They verified their methods worked by checking them against problems where the answer could be determined independently. This is essentially proof by validation. If a method consistently gives correct answers when checked against known results, you can trust it to give correct answers for new problems. This is a legitimate form of mathematical reasoning, particularly important in applied contexts where practical reliability matters more than abstract certainty. The Moscow Papyrus problem about the frustum volume that we mentioned earlier is particularly interesting because it's not clear how the Egyptians derived the formula. Some scholars think they may have used a method involving decomposition, breaking the frustum into simpler shapes whose volumes they could calculate. Others think they may have discovered the formula empirically, by measuring actual frustums and finding the pattern. Either way, the fact that they had the correct formula shows sophisticated mathematical ability. Let's discuss Egyptian contributions to metrology, the science of measurement. Having a standardized measurement system is crucial for any complex civilization. You need to be able to specify quantities precisely and consistently for trade, construction, taxation, and administration. The Egyptian cubit was standardized with official cubit rods kept in temples. These served as the reference standard, like how we now have official meters kept in laboratories. The existence of standardized measures shows mathematical thinking. It recognizes that measurements need to be consistent and reproducible, and it provides a mechanism for ensuring this consistency. The subdivision of the cubit into smaller units follows a mathematical logic. 1 cubit equals 7 palms. 1 palm equals 4 fingers. This hierarchical structure makes it easy to convert between different units and to specify both large and small measurements precisely. It's similar to our metric system where everything is related by powers of 10, except the Egyptian system used different factors. But the underlying principle, having a systematic relationship between units, is the same. Egyptian mathematics also dealt with rates and proportions. Problems involving the strength of beer, the relationship between grain inputs and bread outputs, and similar questions appear in the papyri. These problems involve ratios and proportional reasoning. If you know that a certain amount of grain produces a certain amount of bread, how much grain do you need to produce a different amount of bread? This is a proportion problem, and it requires understanding that the quantities are related by a constant ratio. This kind of mathematical reasoning is fundamental to many practical applications, from cooking recipes to industrial production. The Egyptians also dealt with what we would call inverse proportion. If 10 workers can complete a task in 20 days, how long would it take 15 workers? Fewer workers means more time, and the relationship is inverse. The Egyptians understood these relationships and could calculate accordingly. This shows they had a sophisticated understanding of how quantities relate to each other, not just how to calculate individual values. Now, let's talk about Egyptian arithmetic more broadly. Beyond the specific techniques of doubling and halving we discussed, the Egyptians developed considerable computational skill. They could handle large numbers when necessary. They could perform multi-step calculations, keeping track of intermediate results. They could check their work by performing inverse operations. All of these skills require not just mechanical calculation ability, but also mathematical understanding of what the operations mean and how they relate to each other. The unit fraction system the Egyptians used, while it might seem cumbersome to us, actually had some advantages. It made certain operations easier and provided a unique representation for fractional quantities that avoided ambiguity. The Egyptians developed extensive tables for decomposing fractions into unit fractions. These tables were reference tools that scribes would use, similar to how we might use logarithm tables or calculators. The existence of these tables shows that Egyptians were systematizing mathematical knowledge, creating resources that would make calculations easier and more reliable. Let's discuss what modern archaeology and archaeoastronomy have revealed about Egyptian mathematical astronomy. The ceiling of the tomb of Sennamet, dating to around 1500 BCE, contains a detailed astronomical diagram showing constellations and decans. This ceiling painting is essentially a star map, and creating it required careful astronomical observations and mathematical calculations to determine the positions and relationships between celestial objects. The precision and detail of such astronomical art demonstrate that the Egyptians were systematically recording and mathematically analyzing celestial phenomena. The temples at Abu Simbel provide another stunning example of Egyptian mathematical astronomy. These temples were carved into a mountainside around 1250 BCE during the reign of Ramesses II. Twice a year, on February 21st and October 21st, sunlight penetrates 65 meters into the temple and illuminates the statues in the inner sanctuary. This solar alignment was carefully planned and required precise astronomical calculations. The builders had to know the exact angles of sunrise on these specific dates and orient the entire temple accordingly. The fact that this alignment still functions today, over 3,000 years later, demonstrates extraordinary mathematical and astronomical precision. Modern scholars have studied the astronomical alignments of numerous Egyptian temples and monuments. Many show deliberate orientation towards specific celestial events like solstices, equinoxes, or the rising of particular stars. Creating these alignments required mathematical calculations, converting astronomical observations into architectural specifications. You observe the position of a celestial object, measure its angle relative to the horizon, and then design your building to align with that angle. Each step involves mathematics. The Egyptian lunar calendar adds another layer of mathematical complexity. While their civil calendar had 365 days, they also maintained a lunar calendar for religious purposes. A lunar month is about 29.5 days long, so 12 lunar months equal only 354 days. Reconciling lunar and solar calendars requires mathematical calculations to determine when to add intercalary months. The Egyptians developed methods for tracking both calendars simultaneously and understanding their relationship. This kind of calendar mathematics appears simple in retrospect, but represents sophisticated temporal reasoning. Let's talk about the mathematical aspects of Egyptian art and symbolism. Egyptian art is highly stylized, following strict conventions about proportion and representation. But these conventions are mathematically based. The canon of proportions for depicting the human figure, with specific body parts occupying specific grid squares, ensures consistency across different sizes and contexts. This is fundamentally an application of similar triangles and proportional scaling. An artist can draw a small sketch on a grid and then reproduce it at monumental scale by maintaining the same grid proportions. The use of symmetry in Egyptian art and architecture also reflects mathematical thinking. Bilateral symmetry, where one half mirrors the other, appears throughout Egyptian design. Creating perfect symmetry requires careful measurement and calculation. You need to ensure that corresponding elements on each side are exactly the same distance from the center line and have exactly the same proportions. The Egyptians achieved remarkable symmetry in structures ranging from small artifacts to massive temple facades. This visual harmony that we find so appealing in Egyptian art is actually a consequence of precise mathematical control. Egyptian hieroglyphs themselves include symbols for mathematical concepts and numbers. The system used different symbols for ones, tens, hundreds, thousands, and so on, up to millions. This is a decimal system, based on powers of 10, much like our modern number system. To write a number, you would draw the appropriate number of each symbol. For example, to write 324, you would draw 300 symbols, 2 10 symbols, and 4 1 symbols. This system is less compact than our place value notation, but it's clear and unambiguous. The interesting thing about Egyptian numerals is that they could be written in different orders and orientations depending on the artistic context. The symbols could be arranged horizontally or vertically, reading left to right or left, to fit the available space and maintain visual balance. This flexibility shows that Egyptians understood the mathematical content was separate from the particular visual representation. The number 324 has the same value regardless of how you arrange the symbols, as long as you have the right quantity of each. This is an abstract understanding of number that goes beyond mere counting. Egyptian mathematics also dealt with sequences and series. Problems in the papyri involve arithmetic progressions, where each term differs from the previous one by a constant amount, and geometric progressions, where each term is a constant multiple of the previous one. Problem 64 of the Rhind Papyrus is particularly famous because it involves dividing 10 loaves among 10 men in geometric progression. This problem requires understanding how to work with ratios and how to sum geometric series. The solution method shows sophisticated algebraic reasoning, even though it's expressed in the Egyptian unit fraction notation. Let's discuss the economic and administrative mathematics of ancient Egypt. Running a complex civilization requires extensive mathematical record keeping and calculation, tax collection, grain storage, workforce management, trade transactions. All of these activities demanded mathematical skills. Scribes kept detailed records using their mathematical training to ensure accuracy and catch discrepancies. The bureaucratic machinery of ancient Egypt was built on a foundation of mathematical competence. Without reliable methods for calculation and record keeping, the state couldn't function effectively. Consider the grain storage system. Egypt's prosperity depended on storing grain during good harvest years to provide food during lean years. Managing granaries required mathematical calculations at every step. How much grain do we have? What's the storage capacity of our facilities? How much do we need to feed the population? How much do we keep in reserve? How much can we trade? All of these questions require quantitative answers, and getting those answers requires mathematics. The Egyptian economy was in a very real sense built on mathematical foundations. Trade is another area where mathematics was essential. When Egyptian merchants traded with other civilizations, they needed to calculate equivalencies between different goods, account for transportation costs, and ensure fair exchanges. Mathematical methods for comparing values and calculating ratios were crucial for commercial success. The spread of Egyptian mathematical knowledge through trade contacts may have influenced the development of mathematics in neighboring civilizations. Mathematical knowledge like trade goods could flow along trade routes, spreading techniques and ideas from one culture to another. The construction projects we've discussed, pyramids and temples, also represent massive economic undertakings that required mathematical planning. You need to calculate material requirements, estimate costs, allocate budgets, and track expenditures. Modern project management uses sophisticated mathematical techniques like critical path analysis and resource optimization. The Egyptians didn't have these formal methods, but they were solving the same fundamental problems. They had to figure out how to complete enormous projects within available resources and timeframes. The success of their construction projects shows they must have had effective methods for this kind of planning. Let's talk about mathematical errors in Egyptian sources because these are actually quite revealing. Occasionally, papyri contain arithmetic mistakes or incorrect applications of methods. These errors tell us that Egyptian mathematics was performed by humans who could make mistakes, not by people mechanically following procedures they didn't understand. The errors are often caught and corrected, showing that Egyptians checked their work and understood when something didn't make sense. The existence of errors and corrections actually demonstrates deeper mathematical understanding than perfect mechanical calculation would. Some problems in the papyri are incompletely solved or have damaged sections where the solution is lost. Modern mathematicians have tried to reconstruct how the Egyptians might have solved these problems, and this exercise has led to interesting insights. Sometimes there are multiple possible methods that could work, and we can't be certain which one the Egyptians used. This reminds us that for any given problem there may be many valid solution paths. Egyptian mathematics, like all mathematics, was creative and involved making choices about how to approach problems. Now let's discuss the legacy of Egyptian mathematics in the medieval Islamic world. When Islamic scholars were translating and preserving ancient knowledge during the medieval period, the Islamic mathematical tradition, which made tremendous advances in algebra, trigonometry, and arithmetic, built partly on foundations that included Egyptian contributions. The transmission of knowledge from ancient Egypt through Greece, and then to the Islamic world and eventually to Europe, represents one of the great stories of how mathematical knowledge accumulates across cultures and centuries. The word algorithm, fundamental to computer science and modern mathematics, comes from the name of the Islamic mathematician al-Khwarizmi. But al-Khwarizmi's work built on earlier traditions including contributions from Egypt, Babylon, India, and Greece. This reminds us that mathematics is a collective human endeavor. No single culture or individual creates mathematics alone. Instead, each generation and culture contributes, adding new techniques, solving new problems, and deepening understanding. Egyptian mathematics is one important thread in this vast tapestry. Let's return to construction one more time, because there's a specific problem that beautifully illustrates Egyptian mathematical thinking. When building a pyramid, you're constantly placing stones at the correct angle to maintain the slope. But how do you check that a stone is at the right angle? The Egyptians used the sect system we discussed earlier, but implementing it required practical tools. One method involved using a plumb bob and a measuring rod. You'd place the stone, hang a plumb bob from a known point, measure the horizontal distance from the plumb line to the stone face, and check that this distance matches what the sect specifies. This is applied trigonometry, converting an angular specification into a practical measurement technique. This kind of practical problem solving, finding ways to implement mathematical specifications using available tools, is a hallmark of engineering. The Egyptians were master engineers, and their engineering success was built on mathematical understanding combined with practical ingenuity. They didn't just know the mathematics, they knew how to use it effectively in the real world with real constraints and limitations. This integration of theory and practice is what made their achievements possible. The relationship between Egyptian mathematics and Egyptian religion is also worth considering. Many mathematical activities in ancient Egypt were tied to religious contexts. Temples employed scribes who performed calculations related to offerings, festival dates, and astronomical observations. The alignment of temples with celestial events had religious significance. The mathematical knowledge required for these activities was thus intertwined with religious practice. This reminds us that in ancient societies, different domains of knowledge weren't as separated as they sometimes are today. Mathematics, astronomy, religion, and practical administration all overlapped and informed each other. The cosmological beliefs of the Egyptians included mathematical elements. The concept of Ma'at, representing order, balance, and cosmic harmony, can be seen as having a mathematical dimension. Mathematics is fundamentally about finding order and patterns, about understanding relationships and structures. In some sense, the mathematical activities of Egyptian scribes were participating in maintaining mat, keeping the world orderly and balanced through accurate calculation and record keeping. This philosophical dimension of mathematics, seeing it not just as a tool, but as a way of understanding cosmic order, gives another perspective on why the Egyptians invested so much effort in developing mathematical capabilities. Let's discuss how Egyptian mathematics relates to contemporary mathematics education. One lesson from Egyptian mathematics is the value of concrete, practical problems as a context for learning. Egyptian students learnt mathematics by working through problems about real situations, dividing bread, measuring fields, calculating volumes. This contextualized learning helps students understand why mathematics matters and how it applies to the world. Modern mathematics education sometimes struggles with abstraction that's divorced from application. The Egyptian approach, learning mathematics through meaningful problems, offers an alternative model. Another lesson is the value of multiple representations and methods. The Egyptians had different ways of approaching problems, and they understood that the same answer could be reached by different paths. Encouraging students to explore multiple solution strategies rather than just teaching one standard algorithm can deepen mathematical understanding. The Egyptian doubling method for multiplication, for instance, offers a completely different perspective on multiplication than our standard algorithm. Teaching both can help students understand multiplication more deeply. The Egyptian emphasis on checking and verification is also valuable pedagogically. Egyptian scribes would verify their answers using inverse operations or alternative methods. Teaching students to check their work and to think about whether answers make sense is crucial for developing mathematical competence. Mathematics isn't just about getting answers, it's about understanding processes and being able to evaluate whether results are reasonable. The Egyptian approach embodied this understanding. Egyptian mathematics also reminds us that mathematical notation and methods can vary greatly, while the underlying mathematical content remains the same. Students sometimes think there's only one right way to do mathematics, the way their textbook shows. But actually there are many valid notations and methods, and different approaches have different advantages in different contexts. Exposing students to alternative mathematical systems and notations like Egyptian unit fractions or Egyptian multiplication methods can help them understand that mathematics is more flexible and diverse than it might initially appear. Now let's talk about some ongoing scholarly debates about Egyptian mathematics. One question that historians argue about is how much theoretical understanding the Egyptians had versus purely empirical knowledge. Did they understand why their methods worked? Or did they just know that they worked? This is difficult to answer definitively because the papyri generally don't explain reasoning, just methods. Some scholars argue that the lack of proofs means the Egyptians didn't have deep theoretical understanding. Others argue that the sophistication of their methods implies deeper understanding that simply wasn't recorded in the sources we have. Another debate concerns the relationship between Egyptian and Greek mathematics. How much did Greek mathematicians learn from Egypt? Some ancient sources say that Greek scholars studied in Egypt, but it's hard to know exactly what they learned. The Greek mathematical tradition, with its emphasis on rigorous proof and abstract theory, seems quite different from the practical empirical Egyptian tradition. Yet, there are clear continuities in content, particular geometric knowledge. Understanding the transmission of mathematical knowledge between cultures is complex, and scholars continue to debate the specifics. There's also ongoing research into Egyptian mathematical papyri that haven't been fully studied or translated. New analytical techniques, including advanced imaging that can read damaged or faded text, continue to reveal additional information about Egyptian mathematics. Each new discovery has the potential to change our understanding. The study of ancient mathematics is not a closed field. New evidence can still emerge that forces us to revise our interpretations. Some researchers are using experimental archaeology to better understand Egyptian mathematical practices. They're trying to replicate ancient techniques, building models using Egyptian methods, performing calculations with Egyptian tools, and seeing what challenges arise. This hands-on approach can reveal insights that purely theoretical analysis might miss. For instance, actually trying to lay out a pyramid base using Egyptian surveying techniques helps you understand what problems the Egyptians faced and how clever their solutions were. This kind of experiential research is adding new dimensions to our understanding of ancient mathematics. Let's discuss the relationship between Egyptian mathematics and modern computer science. We mentioned earlier that the Egyptian doubling method for multiplication is similar to how computers multiply numbers, but the connection goes deeper. Egyptian mathematics, with its algorithmic approach and its focus on systematic procedures, has a lot in common with computational thinking. An algorithm is a step-by-step procedure for solving a problem, and Egyptian mathematical methods were algorithmic in this sense. Learning about Egyptian algorithms can actually help students understand what algorithms are and why they're useful. The Egyptian approach to problem solving, breaking complex problems into simpler steps that can be performed systematically, is also fundamental to programming and computer science. When you write a program, you're specifying a sequence of operations that will solve a problem. This is exactly what Egyptian mathematical methods did, just without computers. Teaching Egyptian mathematics to computer science students could help them appreciate the long history of algorithmic thinking and see connections between ancient and modern problem-solving approaches. Let's talk about the tools and instruments that supported Egyptian mathematical practice. We've mentioned Merkit for astronomical observations, cubit rods for standardized measurement, and plumb bobs for checking angles. But the Egyptians also used other tools. They had measuring cords for surveying, which were ropes knotted at regular intervals to allow distance measurement. They had sighting instruments for measuring angles and azimuths. They had sundials and water clocks for measuring time. Each of these tools represents an intersection of mathematics and practical craftsmanship. Someone had to figure out how to construct these instruments so they'd give accurate measurements, and that figuring out required mathematical understanding. The plumb bob is a particularly elegant tool. It's simply a weight on a string, but it provides a perfectly vertical reference line because gravity acts straight down. Using this simple tool, the Egyptians could check whether walls were vertical, establish reference lines for measurements, and solve various geometric problems. The elegance of the plumb bob, using natural forces to provide a mathematical reference, epitomizes the Egyptian approach to practical mathematics. Find simple, reliable methods that work with the materials and forces available. Egyptian mathematics also dealt with three-dimensional spatial reasoning. When you're designing a building or planning a chamber inside a pyramid, you need to think in 3 dimensions. You need to understand how volumes relate, how spaces connect, how structures will look from different viewpoints. Modern architects use computer-aided design software to visualize 3-dimensional spaces. The Egyptians had to develop this spatial reasoning without such aids. They probably used physical models, drawings from multiple perspectives, and careful calculation. The fact that their 3-dimensional designs worked so well shows they had sophisticated spatial and geometric understanding. Let's discuss some of the mathematical challenges the Egyptians faced that we rarely think about. One is material properties. Different types of stone have different densities and strengths. When planning a structure, you need to account for these differences. You need to calculate loads and stresses, even if you don't have modern structural engineering equations. The Egyptians learned through experience which stones could bear which loads, and they incorporated this knowledge into their designs. This experiential knowledge, built up over generations, represented a form of mathematical empiricism: test, measure, calculate, and learn from results. Another challenge is accounting for thermal expansion. Stone expands when heated and contracts when cooled. Over the course of a day, temperature changes can cause measurable dimensional changes in large structures. The Egyptians must have been aware of these effects, even if they didn't quantify them precisely. They designed with tolerance and flexibility to accommodate such variations. Understanding that structures aren't perfectly rigid, that measurements aren't perfectly precise, and that you need to design with margins of error, represents sophisticated engineering thinking informed by mathematical understanding. The logistics of construction present mathematical challenges we've touched on but are worth emphasizing. Coordinating thousands of workers, ensuring materials arrive when needed, sequencing operations so different teams aren't interfering with each other. All of this requires planning and calculation. The mathematics of logistics and operations management, which we now formalize with techniques like linear programming and network analysis, was being done by Egyptian project managers in some form. They may not have had the formal mathematics, but they were solving the same optimization problems. Let's talk about Egyptian contributions to the concept of mathematical proof. While the Egyptians didn't develop the formal deductive proofs that became central to Greek mathematics, they did use verification methods that represent a form of empirical proof. If you can show that a method works correctly for many different cases, especially if you can explain why it should work, you've provided evidence for its validity. This is close to the modern concept of mathematical induction, where you prove something works for a base case and then show it works for the next case, thereby proving it works for all cases. The Egyptian approach of validating methods through repeated successful application is a legitimate form of mathematical reasoning. There's also evidence that Egyptians understood the concept of impossible problems. Some papyrus problems seem to be posed in ways that have no solution, and the scribe recognizes this. Understanding that certain mathematical questions don't have answers, or that certain conditions lead to contradictions, requires sophisticated logical thinking. You need to understand not just how to solve problems but also the structure of problems themselves. This meta-mathematical understanding, thinking about mathematics rather than just doing mathematics, represents a high level of mathematical sophistication. Egyptian mathematics also dealt with optimization in a practical sense. When building a pyramid, you want to use materials efficiently. You want to minimize the amount of cutting and fitting needed. You want to organize workflows so labor is used efficiently. These are optimization problems, finding the best solution given constraints. Modern optimization theory uses calculus and linear programming. The Egyptians used experience, trial and error, and mathematical reasoning, but they were addressing the same fundamental questions. How can we achieve our goals most efficiently given the resources available? The concept of scale models in Egyptian practice represents another interesting mathematical aspect. Before building a full-size structure, you might create a small model to visualize the design and identify problems, but working with scale models requires understanding similarity and proportional relationships. If the model is 1/50th the size of the final structure, every dimension must be scaled by the same factor. Angles remain the same, but lengths, areas, and volumes all scale differently. Understanding these scaling relationships is mathematics, and using scale models effectively requires this mathematical understanding. Let's discuss the social organization required to maintain mathematical knowledge across generations. Mathematics doesn't preserve itself. It must be taught, practiced, and passed down. The Egyptian scribal schools served this function, creating a system where mathematical knowledge was reliably transmitted from masters to students. This institutional framework for preserving and advancing knowledge is itself a remarkable achievement. Many ancient civilizations lost knowledge over time because they didn't have effective systems for transmission. Egypt's long continuity partly reflects its success in maintaining knowledge systems, including mathematical knowledge. The standardization of mathematical methods also required social organization. For Egyptian mathematics to be useful across the entire civilization, scribes in different locations needed to use the same methods and units. This standardization required some form of central authority or shared training that ensured consistency. The existence of standard cubit rods kept in temples, the similarity of methods found in Papyrus from different times and places, all suggest that Egyptian mathematics was systematically standardized. This standardization is what allowed Egyptian civilization to function as a unified administrative entity despite its large size. Let's return to the astronomical achievements one more time, because there's something profound here about the human drive to understand the cosmos through mathematics. The ancient Egyptians looked up at the night sky and saw not just random points of light, but patterns, regularities, and connections. They tracked these celestial phenomena mathematically, recording positions, measuring angles, noting cycles. This impulse to find mathematical order in natural phenomena is fundamentally scientific. It's the same impulse that drives modern astrophysics and cosmology, just with far more primitive tools. The Egyptian recognition that celestial events could be predicted through mathematical calculation represents a crucial insight. It means the universe operates according to rules, not randomly or through the whims of capricious deities. This is a philosophical breakthrough as much as a mathematical one. If you can predict when a star will rise or when the Nile will flood through calculation, you've discovered that the world is comprehensible, that it follows patterns that human reason can understand. This insight underlies all of science and mathematics. Now, let's pull back and consider the big picture. Ancient Egyptian civilization lasted roughly 3,000 years. Throughout this enormous span, mathematical knowledge was preserved, applied, and presumably advanced. The mathematics we see in papyri from different periods shows both continuity and development. Basic methods remained stable, but applications became more sophisticated. This represents successful intergenerational transmission of knowledge on a time scale we can barely comprehend. Modern science and mathematics have only been developing in their current form for a few centuries. The Egyptians maintained their mathematical tradition 10 times longer. What allowed this continuity? Part of it was the stability of Egyptian civilization, which despite political changes and periods of disruption maintained its core cultural identity. Part of it was the institutional structure of scribal schools and temples that preserved and taught knowledge. Part of it was the practical utility of mathematics, which meant there was always motivation to maintain and apply mathematical skills. And part of it was the value Egyptian culture placed on knowledge and learning. Scribes were respected, educated individuals who could rise to positions of power and influence. This social validation of mathematical knowledge helped ensure its preservation. Let's talk about what modern mathematics education might learn from the Egyptian example. First, the integration of mathematics with practical application. Egyptian students learned mathematics in the context of problems they would actually face in their careers. This made the subject relevant and meaningful. Modern mathematics education often struggles with the question of relevance. Students ask why they need to learn certain topics, and sometimes the honest answer is that they probably won't use this particular technique directly. But if we can better integrate practical applications, if we can show students how mathematical thinking helps solve real problems, we might improve both motivation and understanding. Second, the Egyptian emphasis on systematic methods and procedures. Mathematics isn't just about getting answers, it's about having reliable procedures that work consistently. The algorithmic nature of Egyptian mathematics, with clear steps to follow for different problem types, provides structure that can be reassuring for learners. Modern mathematics education sometimes emphasizes conceptual understanding at the expense of procedural fluency, or vice versa. The Egyptian approach suggests that both are important and can be integrated effectively. Third, the use of worked examples and variations. Egyptian mathematical education relied heavily on working through example problems, and then variations on those problems. This is actually consistent with modern cognitive science research on learning, which shows that worked examples are highly effective for developing expertise. Seeing how experts solve problems helps learners develop their own problem-solving skills. The Egyptian pedagogical approach, though ancient, aligns well with what we now know about effective teaching and learning. Fourth, the emphasis on verification and checking, teaching students to verify their answers, to think about whether results make sense, to use alternative methods to check work. These are important mathematical practices. The Egyptian tradition of verification shows that this has always been part of good mathematical practice. In our modern era of calculators and computers, we can sometimes forget the importance of human verification. The Egyptian example reminds us that checking and verification are fundamental mathematical skills, not optional extras. Let's discuss how Egyptian mathematics relates to mathematical creativity. Sometimes ancient mathematics is presented as purely procedural, just following set methods without creativity or insight. But this is a misconception. Developing new methods for solving problems, finding clever ways to apply existing techniques to new situations, recognizing patterns and relationships. These are all creative acts. The Egyptians, who first figured out how to calculate the area of a circle, who developed the seat system for measuring slopes, who designed the pyramids, were being mathematically creative. They were solving problems that had never been solved before, using ingenuity and insight. Mathematical creativity isn't limited to professional mathematicians or modern times. Anyone solving a problem in a new way is being creative. Anyone recognizing a pattern or connection that wasn't obvious is being creative. Egyptian scribes working through problems in their daily practice were regularly engaging in small acts of mathematical creativity. This reminds us that mathematics is fundamentally a creative human activity, not just mechanical symbol manipulation, and it suggests that mathematics education should foster creativity, encouraging students to find their own solution paths and make their own connections, not just memorize procedures. Let's talk about measurement uncertainty and error analysis, topics that are important in modern science and engineering. The Egyptians must have understood that measurements aren't perfectly precise. When you measure a distance with a knotted rope, there's some uncertainty. The rope might stretch. The knots might not be perfectly evenly spaced. You might not read the measurement perfectly accurately. Understanding and working with measurement uncertainty is crucial for practical mathematics. You need to know how precise your measurements need to be for a given application. You need to understand how errors in measurement propagate through calculations. While we don't have explicit Egyptian discussions of measurement error, their successful practical applications imply they understood these issues. They must have known that building the pyramids required more precise measurements than, say, measuring a grain field. They must have had methods for achieving different levels of precision as needed. They must have understood that you need to work with tolerances, accepting small imperfections because perfect precision is impossible. This practical understanding of measurement, even without formal error analysis theory, represents sophisticated mathematical thinking. The Egyptian concept of mathematical beauty is worth considering. While we don't have explicit Egyptian writings on the aesthetics of mathematics, we can infer something from their architectural and artistic work. The Egyptians clearly valued symmetry, proportion, and geometric harmony. The mathematical ratios embedded in their architecture, the careful proportions in their art, the geometric sophistication of their designs, all suggest they found mathematical relationships aesthetically pleasing. This connection between mathematics and beauty, the idea that mathematical order is inherently beautiful, is something many mathematicians still feel today. The Egyptians may have been among the first to recognize and deliberately create this mathematical beauty. Consider the visual impact of the pyramids. Part of what makes them impressive is their mathematical perfection. The clean lines, the precise angles, the massive scale combined with geometric simplicity, these create a powerful aesthetic effect. But this aesthetic effect is entirely dependent on the mathematical precision of the construction. If the pyramids were sloppily built with irregular angles and misaligned faces, they wouldn't have the same impact. The beauty of the pyramids is mathematical beauty made tangible in stone. The Egyptians understood that mathematics could create beauty, and they used this understanding in their monumental architecture. Let's discuss the limits of Egyptian mathematics, not to diminish their achievements, but to understand the boundaries of their mathematical tradition. The Egyptians didn't develop abstract algebra as we know it today. They didn't have negative numbers or the concept of zero as a number. They didn't use variables in the algebraic sense. Their geometry was practical rather than axiomatic. They didn't develop formal logic or set theory. These developments would come later from other mathematical traditions, particularly Greek, Indian, Islamic, and modern European mathematics. Understanding what the Egyptians didn't do is as important as understanding what they did do. It helps us appreciate that mathematical knowledge develops differently in different contexts, and that no single culture develops all aspects of mathematics. The Egyptian focus on practical computational mathematics produced tremendous achievements in engineering and administration, but it didn't naturally lead to the kind of abstract theoretical mathematics that emerged in other traditions. Different cultural needs and intellectual traditions produce different mathematical emphasis. The global mathematical tradition we have today is a synthesis of contributions from many cultures, each bringing different perspectives and techniques. The question of why Egyptian mathematics took the form it did is interesting to consider. Why did they focus on practical computation rather than abstract theory? Probably because the practical approach met their needs effectively. The problems Egyptian civilization needed to solve, construction, administration, trade, astronomy for practical purposes, were all amenable to the computational methods they developed. There was less incentive to develop abstract theory because the practical methods worked well. This doesn't mean Egyptians were incapable of abstract thinking, just that their mathematical tradition emphasized what was useful for their purposes. This raises an interesting question about how mathematical traditions develop. Is mathematics discovered or invented? Do mathematical truths exist independently of human culture, waiting to be discovered, or are they human creations? The Egyptian example suggests a complex answer. On one hand, the mathematical relationships they worked with, like the area of a circle or the properties of triangles, exist independently. The Egyptians discovered these relationships. On the other hand, their particular way of expressing and working with these relationships, their unit fraction system and doubling methods, were cultural inventions. The mathematics itself may be universal, but mathematical practice is culturally specific. Let's return to construction to discuss one more fascinating aspect: the problem of ensuring levelness over large areas. When building a pyramid base that's 230 meters on each side, ensuring that the entire base is level is extraordinarily challenging. Modern construction uses laser levels and sophisticated surveying equipment. The Egyptians probably used water-filled channels as we discussed, but implementing this over such a large area required careful planning and measurement. You need to establish a network of reference points, all at exactly the same elevation, and then you need to cut the bedrock to match this level surface. The mathematical planning required for this operation, figuring out where to place reference points, how to transfer elevations between them, how to verify the accuracy of the leveling, represents sophisticated applied geometry. The fact that the Great Pyramid's base is level to within 2 centimeters over its entire area is almost unbelievable. Think about what that means. You have a base area of over 5 hectares, roughly equivalent to 9 football fields, and the maximum elevation difference is just 2 centimeters. That's a levelness precision of about 1 part in 12,000. Achieving this required not just good methods, but also meticulous execution. Every measurement had to be done carefully, every reference point had to be established accurately, every step of the process had to be checked and verified. This level of quality control in ancient construction is remarkable and speaks to the mathematical culture that guided Egyptian engineering. Let's talk about the mathematics of material estimation. When planning a pyramid, you need to know how much stone you'll need. This requires calculating the volume of the pyramid and then figuring out how many stones of various sizes that volume represents. The volume calculation itself requires understanding that the volume of a pyramid is 1/3 the base area times the height. Did the Egyptians know this formula? The Moscow Papyrus shows they knew the formula for a truncated pyramid, which is more complex, so they almost certainly knew the simpler pyramid formula. Being able to calculate volumes accurately meant they could estimate material needs and plan quarrying operations accordingly. But material estimation isn't just about total volume. You need to account for waste, because not every stone will be usable. You need to account for different types of stone used in different parts of the structure. The interior might use rougher local limestone, while the outer casing uses fine white limestone from distant quarries. The burial chambers might use granite transported from hundreds of kilometers away. Each material has different properties, costs, and transportation requirements. Managing all of this requires extensive mathematical calculation and record keeping. The logistics of a pyramid project were as mathematically complex as the geometry of the structure itself. Egyptian mathematics also dealt with time calculations. How long will this project take? If you have 10,000 workers and you know how long it takes a team to quarry, transport, and place one stone, you can calculate how long the entire project will take. This kind of workforce planning is essentially operations research, using mathematics to optimize complex processes. The fact that the pyramids were completed, that these multi-decade projects actually finished, suggests the Egyptians were reasonably good at project planning and scheduling. Major errors in time estimation would have resulted in projects running indefinitely or being abandoned incomplete. Let's discuss the mathematical aspects of quarrying. Extracting large stone blocks from bedrock requires understanding the properties of stone. You need to identify natural weaknesses in the rock, planes where the stone is likely to split cleanly. You need to calculate where to place wedges or chisels to encourage the stone to break along desired lines. You need to size blocks appropriately, large enough to be structurally useful but not so large that they can't be moved. All of this involves spatial reasoning and understanding of material properties, topics that sit at the intersection of mathematics, physics, and practical experience. The transportation of massive stones is another area where mathematics meets engineering. Moving an 80-ton block of granite hundreds of kilometers requires careful planning. How many people do you need to pull or push it? What kind of sledge or rollers should you use? What path should you take to minimize the energy required? While the Egyptians didn't have our modern physics equations for force, friction, and work, they understood these concepts empirically. They knew that wet sand reduces friction, making it easier to pull sledges. They knew that ramps and leverage could multiply human strength. They knew that distributing loads properly prevents braking. This practical physical understanding guided their mathematical calculations about what was possible. Let's talk about the mathematical education of Egyptian children. Not all children received mathematical education, only those being trained as scribes. But for those who did, what was the experience like? Based on surviving educational materials, students spent years practicing arithmetic, copying problems, and learning standard methods. The training was rigorous and demanding, but it produced highly capable calculators. The educational philosophy seems to have emphasized practice and mastery. Do the same type of calculation repeatedly until it becomes automatic. Then move on to more complex problems. This is similar to how musicians practice scales or athletes practice basic movements, building foundational skills through repetition. The relationship between teacher and student in Egyptian mathematical education was probably highly personal. A master scribe would take on apprentices, teaching them not just mechanical calculation, but also the judgment and understanding needed to apply mathematics effectively. This apprenticeship model, where knowledge is transmitted through close personal interaction, has strengths and weaknesses. It can provide individualized instruction and pass on tacit knowledge that's hard to write down, but it limits how many students can be trained and can allow knowledge to be lost if the chain of transmission breaks. The Egyptian system apparently worked well enough to maintain mathematical knowledge for 3 millennia, so it must have been fairly robust. Let's consider the economics of Egyptian mathematics. Mathematical skills were valuable, and scribes were compensated for their expertise. This created economic incentives for learning mathematics and maintaining high standards of mathematical practice. If being a skilled scribe meant a comfortable life and social respect, young people had reason to invest effort in learning mathematics. This market for mathematical skills helped sustain the educational system and ensured that mathematical knowledge was valued and preserved. In societies where mathematical skills aren't economically valuable, mathematical knowledge tends to decline. The Egyptians created a society where mathematics mattered economically, and this helped ensure its flourishing. The cost of education was also a factor. Training to be a scribe took years and required resources. Families had to be able to support children through years of study, or there had to be institutional support from temples or the state. This meant that mathematical education was somewhat exclusive, limited to families who could afford it or children who received sponsorship. The exclusivity of mathematical knowledge gave it prestige, but also limited the number of mathematically trained individuals. This had implications for how mathematical knowledge developed and spread within Egyptian society. Let's discuss the use of tables and reference materials in Egyptian mathematics. We mentioned earlier that Egyptians had tables for decomposing fractions into unit fractions. They probably also had tables for other purposes. conversion factors between different units, standard areas and volumes for common shapes, perhaps astronomical tables showing positions of celestial objects. These reference materials served as tools that made mathematical work more efficient. You didn't need to recalculate everything from first principles if you could look up common values in a table. This use of pre-computed tables is very much in the spirit of modern scientific calculation, where we rely extensively on reference data and computational tools. Creating accurate tables is itself a mathematical task. Someone had to perform the calculations initially, verify their accuracy, and record them in a form that others could use. This represents a form of mathematical research and development. The scribes who created these tables were advancing mathematical practice by making calculations easier for future generations. This accretion of tools and techniques over time is how mathematical traditions develop and improve. Each generation inherits tools from the previous generation, uses them, and perhaps adds new tools that the next generation will inherit. Let's talk about Egyptian contributions to the mathematical concept of infinity. Did the Egyptians think about infinity? Their number system could express very large numbers up to millions. But did they have a concept of numbers continuing indefinitely, of processes that never end? We don't have clear evidence one way or another. The practical focus of Egyptian mathematics might not have led them to contemplate infinite processes, but they did deal with division problems that today we would say have infinite decimal expansions. When they decomposed fractions into unit fractions, they were finding finite representations for quantities we might express differently. Their approach avoided some of the philosophical puzzles about infinity that later mathematicians would grapple with. The Egyptian relationship with very large numbers is interesting. The largest number in their regular system was 10 million, but they had a hieroglyph representing many or countless used for quantities beyond specific enumeration. This suggests they recognized there were quantities larger than their number system easily expressed, even if they didn't formalize the concept of infinity. The recognition that numbers can be larger than our ability to count or calculate, that there are quantities beyond our practical grasp, is a step toward understanding infinity. Let's discuss how Egyptian mathematics handled complexity. When you have a problem with many interrelated factors, how do you approach it? The Egyptian method seems to have been decomposition, breaking complex problems into simpler subproblems. This is a powerful strategy that remains fundamental to problem solving today. In computer science, we call it divide and conquer. In project management, we call it work breakdown structure. The Egyptians were applying this principle thousands of years ago, understanding that complexity can be managed by breaking it down into manageable pieces. Consider planning a pyramid project. The overall task is enormously complex, involving quarrying, transportation, construction, workforce management, resource allocation, and more. The Egyptian approach was apparently to break this down into subtasks, each of which could be planned and managed separately while maintaining coordination of the whole. This hierarchical approach to complexity, managing at multiple levels of detail simultaneously, is sophisticated organizational thinking, informed by mathematical understanding of how complex systems can be structured. Let's talk about errors and failures in Egyptian construction, because these are informative. Not every Egyptian construction project succeeded perfectly. Some pyramids show evidence of changes in design during construction. Some structures partially collapsed and had to be repaired or modified. These failures, while unfortunate, represent learning opportunities. Each failure taught the Egyptians something about structural limits, about what works and what doesn't. The mathematical models and methods they used were refined over time based on experience. This empirical approach, learning from both successes and failures, is fundamental to engineering progress. The bent pyramid at Dashur is a famous example. This pyramid starts at a steep angle, but then shifts to a shallower angle partway up. Most scholars think the original angle was proving unstable, and the builders changed the angle to ensure the structure wouldn't collapse. This represents responsive problem solving. When the mathematics and engineering revealed a problem, they adapted. The bent pyramid still stands today, testimony to the Egyptians' ability to recognize and solve problems, even mid-project. Mathematical understanding, isn't just about planning perfectly from the start. It's also about being able to analyze problems as they arise and find solutions. Let's discuss the mathematical aspects of Egyptian medicine. Egyptian physicians used mathematics in various ways. They calculated dosages for medicines based on patient weight and condition. They measured pulse rates and breathing rates to assess health. They understood some quantitative relationships between symptoms and treatments. Medical papyri contain numerical prescriptions and measurements. This represents an early form of quantitative medicine using numbers to guide treatment decisions. While Egyptian medicine was mixed with magic and religion, there was also a practical quantitative component that used mathematical thinking. The Edwin Smith Papyrus, a medical text dating to around 1600 BCE, contains surgical descriptions with measurements and quantitative observations. It describes examining wounds, measuring their size, and making treatment decisions based on these observations. This clinical approach, using measurement and observation to guide decisions, is fundamentally mathematical in spirit. It recognizes that quantities matter, that careful measurement provides information that can improve outcomes. This mathematical approach to medicine was remarkably advanced for its time. Let's talk about Egyptian understanding of rates and ratios in practical contexts. When making beer, the strength of the beer depends on the ratio of grain to water and the fermentation process. Egyptian beer makers would have understood these relationships quantitatively, even if they expressed them differently than we would. When mixing materials for construction mortar, ratios matter. When calculating how much food to provide workers based on the amount of work performed, you're dealing with rates. The Egyptians handled these quantitative relationships effectively, showing they understood proportional reasoning in diverse contexts. The concept of pefsu, used in ancient Egypt to measure the strength of beer or bread, is an interesting example of a ratio. The pefsu indicates how many loaves of bread or jugs of beer you get from a unit quantity of grain. A lower pefsu number means stronger beer or denser bread, because less product is produced from the same amount of grain. This is essentially an inverse ratio, and using it requires understanding how quantities relate inversely. Problems involving pefsu appear in the mathematical papyri, showing that this kind of proportional reasoning was part of mathematical education. Let's discuss the mathematical sophistication required for Egyptian irrigation systems. Egypt depended on managing Nile water for agriculture. This required canals, basins, dams, and control structures. Designing and maintaining irrigation systems requires understanding fluid flow, volumes, slopes, and timing. How much water do your fields need? How large should your storage basins be? What slope do your canals need to ensure water flows properly? The mathematics of water management is complex, involving both geometry and what we would now call fluid mechanics. The Egyptians developed practical methods for these calculations. Based on experience and observation, the nilometer is an interesting example of quantitative water management. This was a structure for measuring the Nile's water level, with markings indicating flood heights. By tracking water levels over years, the Egyptians could predict flood severity and adjust their agricultural plans accordingly. They could also use water level measurements to calculate volumes of water stored in reservoirs or flowing through canals. The nilometer represents a quantitative approach to managing natural variation, using measurement and mathematical calculation to inform decisions. Let's talk about how Egyptian mathematics handled symmetry and transformations. Egyptian art and architecture show extensive use of symmetry, as we've discussed, but creating symmetrical designs requires understanding geometric transformations like reflection and rotation. When you create a design for one side, and then want to mirror it on the other side, you're performing a reflection transformation. The Egyptians didn't have our formal language for describing transformations, but they clearly understood them intuitively and could execute them precisely. This geometric understanding was fundamentally mathematical, even if expressed through artistic and architectural practice rather than abstract theory. The use of grids in Egyptian art is related to this. A grid provides a coordinate system that makes it easier to reproduce designs and maintain proportions. When you want to scale a design from a small model to a large wall painting, The grid helps you transfer each element to the correct position at the correct size. This is coordinate geometry in practice, using a systematic framework to organize spatial information. The Egyptians invented practical coordinate systems long before Descartes formalized the concept in the 17th century. Let's discuss the relationship between Egyptian mathematics and Egyptian technology. Technology provides tools that enable new mathematical applications, and mathematics enables new technologies. The Egyptians had technologies for working stone, for smelting and casting metals, for making papyrus and ink, for constructing boats and wheels and pulleys. Each of these technologies involved quantitative considerations. How hot does copper need to be to smelt it? What proportions of copper and tin produce good bronze? How thick does papyrus need to be for writing? These aren't purely mathematical questions, but they have quantitative components that benefit from mathematical thinking. The wheel and axle used in Egyptian pottery wheels and transportation devices represent an understanding of mechanical advantage and rotational motion. These concepts have mathematical aspects related to ratios and circular geometry. The lever, used in shaduf devices for lifting water and in construction for moving heavy objects, represents understanding of proportional relationships between force, distance, and pivot point. Egyptian engineers understood these mechanical principles practically, even without formal physics equations. Their technology was informed by intuitive understanding of quantitative relationships that we would now express mathematically. Let's talk about papyrus itself. As a technology supporting mathematics, papyrus provided a relatively inexpensive writing surface compared to carving on stone or working with clay tablets. This made it more practical to perform calculations, create tables, and record information. The availability of papyrus as a medium probably influenced the development of Egyptian mathematics by making mathematical practice more accessible. You could work through problems on papyrus, make mistakes and correct them, create drafts and copies. This flexibility supported mathematical learning and practice in ways that more permanent or expensive media would not. The ink and writing implements used by Egyptian scribes also mattered. The ability to write clearly in hieratic script with reed pens allowed for relatively rapid notation compared to carving hieroglyphs. This made it practical to perform multi-step calculations following procedures that required many intermediate steps. The physical tools of writing and calculation aren't separate from mathematical practice. They shape what's possible and what's convenient, thereby influencing how mathematics develops and what problems people choose to tackle. Let's discuss Egyptian understanding of periodicity and cycles. The Egyptians recognized many cyclic patterns in nature: the annual Nile flood, the daily motion of the sun, the monthly phases of the moon, the yearly cycle of seasons, the multi-year cycles of certain celestial phenomena. Understanding and predicting these cycles required mathematical methods for tracking time and extrapolating patterns. The concept of periodicity, that certain phenomena repeat in regular patterns, is fundamentally mathematical. Recognizing periodicity allows prediction, and prediction allows planning. The Egyptian calendar system represents their mathematical modeling of cyclic time. The concept of a cycle implies a unit that repeats. A day is a cycle, a year is a cycle, but cycles can nest within each other. Days within months, months within years. Understanding these hierarchical cycles requires mathematical thinking about how different timescales relate. The Egyptian calendar's structure, with its 12 30-day months plus 5 extra days, represents a mathematical model that approximates the true solar year while maintaining a simple structure. It's not perfect. The solar year is actually 365 1/4 days, but it's close enough for most purposes, and much easier to work with than a more accurate but complex calendar would be. Let's talk about the mathematical concept of a standard or unit. Egyptian mathematics relied on standardized units for measurement, cubits for length, hecate for volume, dibin for weight. Having standard units is fundamental to quantitative thinking. Without standards, you can't compare measurements, you can't share specifications, you can't coordinate work across different people and places. The creation and maintenance of measurement standards represents mathematical thinking about what it means to measure and how to ensure measurements are consistent. The cubit rods kept in temples as physical standards show that the Egyptians understood the importance of maintaining consistency in measurement. But standardization also requires authority and enforcement. Someone has to decide what the standard is and ensure people follow it. The social and political organization required to maintain measurement standards is an interesting complement to the mathematical concepts themselves. Mathematics doesn't exist in a vacuum. It exists within social systems that support or constrain mathematical practice. The Egyptian state, with its centralized authority and extensive bureaucracy, provided a framework within which mathematical standardization could be implemented and maintained. Let's discuss the question of whether Egyptian mathematical knowledge was esoteric or public. Were mathematical methods closely guarded secrets known only to a priestly or scribal elite? Or were they more widely known? The evidence suggests a middle position. Mathematical knowledge was specialized, requiring years of training to master, but it wasn't secret in the sense of being deliberately hidden. Scribes needed to share knowledge to coordinate work. Mathematical methods were taught systematically in schools, not passed down through secret initiation. The papyri that survive are essentially textbooks designed to teach methods to students. This suggests Egyptian mathematics was expert knowledge but not secret knowledge. The distinction matters because it affects how mathematical knowledge develops and spreads. Secret knowledge tends to stagnate because the pool of people who can contribute is small and isolated. Expert knowledge that's widely shared among specialists but not secret can develop more dynamically as specialists share insights and techniques. The Egyptian mathematical tradition seems to have been expert knowledge of this latter type, which helps explain how it could develop and be maintained over such a long period. Let's talk about mathematical errors and misconceptions in Egyptian mathematics. Did the Egyptians believe anything that we would now recognize as mathematically wrong? It's hard to say for certain because we have limited sources, but we can make some educated guesses. Their approximation for pi was slightly off, but they may not have thought of it as an approximation at all, just as a working formula. Their fraction system, while valid, made some operations more difficult than they need to be, but that's more a question of efficiency than correctness. For the most part, the mathematical methods we see in Egyptian sources are mathematically sound, just expressed differently than we would express them. This raises an interesting point about mathematical truth. There are mathematical relationships that are objectively true. The sum of angles in a flat triangle is 180 degrees. The area of a circle with radius r is pi r squared. These truths don't depend on culture or notation, but the way we discover, express, and use these truths can vary enormously across cultures. The Egyptians were working with the same mathematical realities we work with, but they approached them differently. Understanding this helps us appreciate both the universality of mathematical truth and the diversity of mathematical practice. Let's discuss how Egyptian mathematics related to probability and uncertainty. Did the Egyptians think about probability? We don't have clear evidence that they formalized probability concepts, but they certainly dealt with uncertainty in practical ways. When planning agricultural yields, they had to account for the fact that harvests vary from year to year. When estimating project timelines, they had to account for unexpected delays. This practical dealing with uncertainty requires some intuitive understanding of variability and risk, even without formal probability theory. The Egyptian practice of maintaining grain reserves shows they understood the need to prepare for unfavorable outcomes, which is fundamentally about managing risk. The Egyptians also played games involving chance elements like throwing sticks or dice. Playing such games requires at least intuitive understanding that some outcomes are more likely than others. Whether they quantified these probabilities or just had a feel for them, we can't say, but the existence of games of chance shows they were comfortable with random outcomes and uncertainty. This comfort with uncertainty in games might not have translated into mathematical probability theory, but it shows they recognized that not everything is predictable or determined. Let's talk about the transmission of Egyptian mathematical knowledge to other cultures. We've mentioned Greek scholars studying in Egypt, but there were probably other transmission pathways as well. Trade connections between Egypt and other ancient civilizations provided opportunities for knowledge exchange, diplomatic exchanges, military conquests, migrations of peoples. All of these could have facilitated the spread of mathematical knowledge. The ancient world was more connected than we sometimes realize, and ideas traveled along with goods and people. Egyptian mathematical techniques might have influenced Babylonian mathematics, or vice versa, or both might have drawn from common earlier sources. Tracing these influences is difficult because direct evidence is scarce, but the connections almost certainly existed. The Hellenistic period, after Alexander the Great conquered Egypt in 332 BCE, saw extensive Greek settlement in Egypt, particularly in Alexandria. This created conditions for intensive cultural and intellectual exchange. The Library of Alexandria famously collected knowledge from across the known world, and Egyptian mathematical texts would have been part of this collection. Greek scholars working in Alexandria had direct access to Egyptian mathematical tradition, and this probably influenced the development of Hellenistic mathematics. The synthesis of Egyptian practical mathematics with Greek theoretical mathematics during this period represents an important moment in the history of mathematics. Let's discuss the role of mathematics in Egyptian religion and cosmology more deeply. We mentioned Maset and cosmic order earlier. The Egyptian cosmos was understood in both mythological and practical terms. The regular motions of celestial bodies, the predictable flooding of the Nile, the cycles of day and night and seasons, all of this regularity suggested an underlying order to the universe. Mathematics was a tool for understanding and describing this order. In this sense, doing mathematics was participating in understanding the cosmic order, aligning human knowledge with divine patterns. This gave mathematical practice a significance beyond mere utility. The orientation of temples and pyramids towards specific celestial points represented an attempt to align earthly structures with heavenly order. This wasn't arbitrary symbolism. It required precise astronomical observation and mathematical calculation. The mathematics was the means by which the alignment was achieved. In this way, mathematics served religious purposes, helping humans create sacred spaces that connected earth and heaven. The mathematical sophistication required for these alignments shows that religious motivations could drive mathematical development just as much as purely practical needs could. Let's talk about what the study of Egyptian mathematics tells us about the nature of mathematical knowledge itself. One lesson is that mathematical knowledge is both discovered and constructed. The Egyptians discovered mathematical relationships that exist objectively, geometric facts, arithmetical patterns, astronomical regularities. But they also constructed ways of expressing and working with these relationships, their notation, their methods, their conceptual frameworks. This discovery-construction duality is characteristic of mathematics generally. We work with realities that exist independently of us, but we create the intellectual tools we use to engage with those realities. Another lesson is that mathematical knowledge is cumulative but also sometimes forgotten and rediscovered. The Egyptian mathematical tradition lasted 3 millennia, but eventually declined as Greek and Roman influences became dominant. Some Egyptian mathematical knowledge was preserved through Greek sources, but some was probably lost. Later mathematicians rediscovered techniques that Egyptians had known without necessarily being aware of the earlier discovery. This pattern of knowledge gained, lost, and regained is common in history. It reminds us that preserving and transmitting knowledge requires ongoing effort and institutional support. Knowledge isn't automatically preserved just because it once existed. Let's discuss how Egyptian mathematics relates to modern STEM education. STEM stands for science, technology, engineering, and mathematics, and these fields are increasingly emphasized in modern education. The Egyptian example shows that these domains have always been interconnected. Egyptian mathematics was developed primarily for technological and engineering applications. It served scientific purposes in astronomy and medicine. The boundaries between these fields were fuzzy or non-existent. This integrated approach, where mathematical knowledge is developed and applied across multiple domains simultaneously, is arguably closer to how STEM should be taught than the often siloed approach modern education takes. When students learn mathematics in isolation from applications, it can seem abstract and pointless. The Egyptian approach, where every mathematical method had clear practical purpose, made the relevance of mathematics obvious. Modern STEM education is trying to recapture this integration through project-based learning, where students work on complex problems that require knowledge from multiple fields. The Egyptian example suggests this integration is natural and effective. Mathematics developed to solve real problems, and teaching it in that context helps students understand why mathematical knowledge matters. Let's talk about the computational complexity of Egyptian mathematical methods. In modern computer science, we analyze algorithms by how efficiently they solve problems as problem size grows. The Egyptian doubling method for multiplication, for example, is quite efficient. It requires only as many steps as there are powers of 2 in one of the numbers being multiplied, which grows logarithmically with the size of the number. This is actually comparable to or better than the efficiency of the multiplication algorithms most people learn in school. The Egyptians developed an efficient algorithm even though they weren't thinking about it in terms of computational complexity. The unit fraction decomposition methods, on the other hand, can be less efficient. Finding a unit fraction representation for a given fraction might require considerable trial and error, and the resulting representation might require many terms. For practical purposes, having tables of common decompositions helped avoid the need to compute from scratch, but the method itself is less efficient than working with fractions in our standard form. This illustrates an important point. Different mathematical methods have different efficiency trade-offs, and sometimes practical considerations like having good reference tables matter more than theoretical efficiency of the basic algorithm. Let's discuss the geometric sophistication visible in Egyptian decorative arts. Beyond architecture, the Egyptians created intricate geometric patterns in jewelry, textiles, pottery, and wall decorations. These patterns often involve regular tessellations, where geometric shapes fit together to fill a surface without gaps or overlaps. Creating successful tessellating patterns requires understanding of geometric relationships and symmetry. Some tessellation patterns are straightforward, like regular grids of squares or triangles. Others are more complex, involving multiple shapes or more subtle symmetries. The Egyptians explored a rich variety of geometric patterns, demonstrating sophisticated understanding of plane geometry. The use of geometric patterns in Egyptian art also reflects aesthetic preferences that valued order, symmetry, and mathematical regularity. The visual appeal of geometric patterns is related to their mathematical properties. Pattern and repetition create a sense of order and harmony. Symmetry creates balance. These aesthetic effects are mathematical effects, showing how mathematics can serve artistic purposes. The integration of mathematics and art in Egyptian culture is complete. They weren't separate domains but different aspects of a unified approach to creating beautiful, ordered, meaningful objects and spaces. So here we are, having journeyed through the shocking secrets of ancient Egyptian mathematics. We've seen how the Egyptians developed sophisticated mathematical techniques for construction, astronomy, administration, and more. We've explored their unique approaches to arithmetic, their geometric insights, their astronomical calculations. We've seen how their practical, empirical approach to mathematics enabled them to build some of the most impressive structures in human history and maintain a civilization for 3,000 years. We've learned that mathematical sophistication can take many forms, and that the Egyptians, working without our modern tools and notation, achieved remarkable mathematical feats. The foundational contributions of Egyptian mathematics to human knowledge are immense. They developed methods that influenced later mathematical traditions. They demonstrated that human reason could understand and predict natural phenomena. They showed how mathematics could be used to achieve engineering marvels. They created an educational system that preserved and transmitted mathematical knowledge across generations. Their achievements stand as testament to human intellectual capability and the power of mathematical thinking. But beyond the specific mathematical techniques and achievements, Egyptian mathematics teaches us something deeper about the nature of knowledge and civilization. It shows us that building a lasting, prosperous civilization requires more than physical resources or military power. It requires knowledge, particularly mathematical knowledge, that enables you to measure, calculate, plan, and build. It requires educational systems that transmit knowledge across generations. It requires institutions that value and support intellectual work. It requires a culture that recognizes the importance of precision, accuracy, and systematic thinking. The ancient Egyptians understood these things. They invested heavily in mathematical education, trained skilled scribes, maintained measurement standards, and applied mathematical methods systematically across their society. This investment paid off in the form of architectural wonders that still inspire awe, administrative systems that managed a large and complex state, agricultural systems that fed millions, and astronomical knowledge that tracked the heavens. The correlation between their mathematical sophistication and their civilizational success is not coincidental. Mathematics enabled their achievements. So what can we take away from this deep dive into Egyptian mathematics? First, we should appreciate the sophistication and ingenuity of ancient peoples. The Egyptians weren't primitive. They were highly intelligent people who developed effective solutions to complex problems using the tools and knowledge available to them. Our modern advantages come from accumulated knowledge and technological tools, not from being inherently smarter than our ancestors. Recognizing this should make us both humble about our own accomplishments and appreciative of what earlier civilizations achieved. Second, we should recognize that there are multiple valid approaches to mathematics. The Egyptian methods looked different from ours, but they worked. Their unit fraction system, their doubling methods, their geometric techniques, all of these were mathematically sound and practically effective. In our increasingly interconnected world, we can learn from diverse mathematical traditions. Different approaches offer different insights, and mathematical knowledge is enriched by diversity. We shouldn't assume that our modern Western mathematical tradition is the only way or even always the best way to approach mathematical problems. Third, we should remember that mathematics is fundamentally practical and purposeful. It exists to help us understand and manipulate the world. While abstract pure mathematics has value and beauty, applied mathematics that solves real problems is what most affects human life. The Egyptian focus on practical applications kept their mathematics grounded and relevant. Modern mathematics education could benefit from emphasizing applications more and abstract theory less, particularly in early education, where motivation and engagement are crucial for developing mathematical interest and confidence. Fourth, we should appreciate the connections between mathematics and other human endeavors. Egyptian mathematics was intertwined with architecture, astronomy, art, religion, economics, and administration. This integration is natural because mathematics is a fundamental tool that applies across domains. Modern education's tendency to compartmentalize knowledge into separate subjects can obscure these connections. Interdisciplinary approaches that show how mathematical thinking connects to diverse fields can make education more effective and help students see the broader significance of what they're learning. Fifth, we should recognize the importance of preserving and transmitting knowledge. The Egyptian mathematical tradition lasted 3 millennia because they had effective systems for teaching mathematics to new generations. Knowledge isn't self-perpetuating. It must be actively maintained, taught, and practiced, or it will be lost. In our modern world with rapidly changing technology and society, ensuring that fundamental knowledge and skills are transmitted effectively is crucial. We can't assume that just because we know something now, it will still be known in the future. Education, documentation, and knowledge preservation require ongoing investment and attention. Sixth, we should be inspired by what human intelligence and determination can achieve. The pyramids stand as monuments to human capability. They show what's possible when knowledge, organization, and persistence combine in service of an ambitious goal. While we have technological advantages the Egyptians lacked, the fundamental human qualities that enabled their achievements, intelligence, creativity, discipline, cooperation, are the same ones we can apply to modern challenges. Whether we're addressing climate change, developing sustainable energy, exploring space, or solving any other complex problem, we need the same combination of mathematical thinking, practical ingenuity, and determined execution that the Egyptians exemplified. Looking at Egyptian mathematics from our modern perspective, we can see both how far we've come and how much we've built on foundations laid thousands of years ago. The abstract algebra and analysis of modern mathematics would be incomprehensible to an ancient Egyptian scribe, but that scribe would recognize the fundamental goal: using mathematical thinking to understand patterns, solve problems, and achieve purposes. The continuity of mathematical endeavor across thousands of years and diverse cultures is one of humanity's great collective achievements. We stand on the shoulders of giants, including the anonymous Egyptian mathematicians and scribes who developed the techniques we've been discussing. The pyramids will stand for thousands more years, barring some catastrophe. They're monuments not just to the pharaohs buried within them, but to the mathematical knowledge that made their construction possible. Every precisely cut stone, every carefully aligned wall, every calculated angle represents the application of mathematical thinking. When you stand before the Great Pyramid and marvel at its scale and precision, you're witnessing mathematics made tangible. The pyramid is a mathematical proof in stone, demonstrating that human reason can understand the world well enough to reshape it according to our purposes. The astronomical alignments of Egyptian temples likewise stand as permanent records of their astronomical and mathematical knowledge. When sunlight penetrates the sanctuary at Abu Simbel on those specific dates, we're witnessing an event that was planned and calculated over 3,000 years ago. The mathematics that made that alignment possible still functions perfectly. These alignments are messages across time, showing future generations what their ancestors knew and could accomplish. In a sense, every precisely aligned temple is a mathematical text written in stone and oriented by the stars, waiting to be read by those with knowledge to understand it. Egyptian mathematical papyri, the Rhind Papyrus and Moscow Papyrus and others, are precious documents that give us direct access to ancient mathematical thinking. Every problem worked out on these papyri, every calculation performed by ancient scribes, when we work through the same problems following the same methods, we're recreating their thought processes. This is an intimate form of historical connection. Mathematics provides a bridge across time because mathematical truths and methods transcend their cultural context. An Egyptian scribe and a modern student solving the same geometric problem are engaged in fundamentally the same intellectual activity, despite the vast gulf of time and culture separating them. This universality of mathematical thinking is profound. Mathematics is a human universal. Every culture that has developed beyond the most basic level has developed mathematical concepts and methods. The specific forms vary, but the underlying impulse to quantify, to measure, to calculate, to find patterns and relationships appears to be fundamental to human cognition. We are mathematical creatures. Our brains seem naturally inclined toward mathematical thinking, even if developing sophisticated mathematical skills requires training and effort. The Egyptian example shows this mathematical capacity flourishing in one particular cultural context, but the capacity itself is universal. So where does this leave us? What's the big revelation we've been building toward? Here it is. Ancient Egyptian mathematics wasn't primitive. It wasn't simple. It wasn't a curious but irrelevant historical footnote. It was sophisticated, effective, and foundational. The mathematical techniques developed in ancient Egypt enabled one of history's most impressive civilizations. Those techniques influenced later mathematical traditions and contributed to the accumulated knowledge that we benefit from today. When modern engineers study the pyramids and marvel at their construction, they're recognizing the sophistication of the mathematical thinking that went into them. When modern educators look for ways to make mathematics more relevant and engaging, they can learn from the Egyptian approach of tying mathematics closely to practical applications. The shocking secret of Egyptian mathematics is that it was shockingly good, against all our modern prejudices about ancient peoples being less capable or intelligent than we are. The Egyptians developed mathematical methods that solved complex problems effectively. They achieved engineering feats that challenge even modern capabilities. They maintained an intellectual tradition for 3,000 years, longer than the entirety of modern science has existed. They deserve our respect and admiration, not condescension or dismissal. But there's another shocking secret, perhaps even more important. An administration were laid thousands of years ago by people using methods that look very different from ours, but were mathematically sound and practically effective. Our modern world, with all its technological sophistication, builds on foundations that stretch back through Islamic mathematics, through Greek mathematics, through Babylonian and Egyptian and Indian mathematics, back into the depths of history. We didn't invent mathematical thinking in the modern era. We inherited it from countless generations of mathematicians, scribes, engineers, and scholars who each contributed their insights to a growing body of knowledge. This is simultaneously humbling and empowering. It's humbling because we have to recognize that we're not as unique or self-made as we might like to think. Our capabilities rest on foundations we didn't build. But it's empowering because it shows that human knowledge can accumulate across vast stretches of time. The work we do today, the knowledge we create, the problems we solve, can benefit people hundreds or thousands of years in the future. Just as we benefit from the work of ancient Egyptians and others, we're part of a multi-generational, multicultural project of building human knowledge and capability. That's both a privilege and a responsibility. The responsibility aspect is crucial. If we benefit from knowledge passed down to us, we have an obligation to preserve it, add to it, and pass it on to future generations. We have an obligation to maintain educational systems that teach mathematical and scientific literacy. We have an obligation to support research that extends knowledge. We have an obligation to apply knowledge wisely in service of human welfare. The Egyptians took these obligations seriously. Their investment in mathematical education, their careful preservation of knowledge, their ambitious applications of mathematical thinking to improve their civilization, all reflect a culture that valued knowledge and understood its importance. Can we say the same about our own culture? Do we invest adequately in education? Do we support the transmission of fundamental knowledge across generations? Do we apply our mathematical and scientific knowledge wisely? These are questions worth pondering. The Egyptian example provides a standard against which we might measure ourselves. A civilization that maintained mathematical knowledge for 3,000 years, that achieved engineering marvels that still stand and inspire, that valued learning and precision and systematic thinking, has lessons to teach us. Let's imagine for a moment what an ancient Egyptian scribe would think of our modern world. They'd probably be amazed by our technology, our computers and smartphones and spacecraft, but I suspect they'd also recognize fundamental continuities. They'd see that we still use mathematics to plan construction projects, just with more sophisticated tools and methods. They'd see that we still observe the heavens trying to understand cosmic order, though now we call it astronomy and astrophysics rather than celestial observation. They'd see that we still face the challenge of transmitting knowledge across generations, ensuring that young people learn what previous generations discovered. They'd recognize our mathematical notation as serving the same purposes their hieratic numerals served, just more compactly and flexibly. In some ways, an Egyptian scribe might feel quite at home in a modern engineering firm or research institution. The fundamental activities, observing phenomena, measuring carefully, calculating precisely, checking results, solving problems, working with colleagues, would all be familiar. The tools would be vastly more advanced, but the intellectual processes would be recognizable. Mathematics creates this continuity across time. The problems change, the methods evolve, but the underlying mathematical way of thinking remains constant. This thought experiment highlights something important. While technology changes rapidly, fundamental human capabilities and challenges change much more slowly. The Egyptians faced challenges of construction, administration, agriculture, trade, and understanding nature. We face the same types of challenges, just in different specific forms. They used mathematics to address these challenges. We do too. The technological details differ enormously, but the fundamental role of mathematical thinking in solving human problems remains constant. This suggests that mathematical literacy isn't just about preparing for specific careers or technologies. It's about developing a way of thinking that's been valuable throughout human history and will likely remain valuable far into the future. The specific mathematical techniques you learn might become obsolete. Egyptian doubling methods for multiplication have been replaced by more efficient algorithms. But the underlying capacities that mathematical education develops, logical thinking, systematic problem solving, precision in reasoning, comfort with abstraction, ability to work with quantitative information, these remain valuable regardless of technological change. This is perhaps the most important lesson from Egyptian mathematics. The value isn't primarily in specific techniques, but in the mathematical way of thinking that those techniques embody and teach. So let me bring this all together with a final thought. The pyramids stand in the Egyptian desert as monuments to what mathematical thinking can achieve. They're not just impressive structures, they're demonstrations of human capability, showing what's possible when knowledge, organization, and determination combine. When you understand the mathematics that went into their construction, the careful calculations of angles and volumes, the precise measurements and alignments, the logistical planning required to move millions of stones, your appreciation for these structures deepens. They become not just visually impressive, but intellectually impressive. They represent the triumph of human reason over raw nature, the ability to envision something that doesn't exist, and then make it real, through systematic application of knowledge and effort. This is what mathematics offers humanity, the ability to understand the world precisely enough to reshape it according to our purposes. The Egyptians understood this. They invested in mathematical knowledge because it gave them power, not military power primarily, but the power to build, to plan, to predict, to organize, to achieve. This power is available to us too. Mathematical knowledge is more accessible now than ever before. We have educational resources the Egyptians couldn't imagine. We have computational tools that make complex calculations trivial. We have accumulated knowledge from millennia of mathematical development. The question is whether we'll use these advantages wisely and well. The shocking secret of Egyptian mathematics is ultimately this: human beings, using intelligence and systematic thinking, can achieve remarkable things. We can build structures that last thousands of years. We can predict celestial events decades in advance. We can organize complex societies and manage scarce resources effectively. We can understand the world well enough to manipulate it successfully. The Egyptians proved this thousands of years ago. They left us monuments of stone and documents of papyrus that testify to their achievements. These monuments and documents are calling out to us across the millennia, reminding us of human capability and challenging us to use our own advantages as effectively as they used theirs. Every time you perform a calculation, solve a problem, or use mathematical thinking to understand something better, you're participating in the same tradition the Egyptian scribes participated in. You're exercising the same fundamental human capability they exercised. You're part of a project that spans all of human history, the project of using mathematical reasoning to understand and improve the world. This is your inheritance from ancient Egypt and countless other mathematical traditions. The question is, what will you do with it? What will you build, literally or figuratively? What problems will you solve? What knowledge will you create and pass on? The Egyptian scribes did their part. Now it's our turn. I encourage you, inspired by what we've learned about Egyptian mathematics, to recognize the value of mathematical knowledge in your own life. Whether you're a student struggling with mathematics classes, a professional using mathematical tools in your work, or just someone trying to understand the world better, remember that mathematics is not just abstract symbol manipulation. It's a powerful tool for understanding and acting in the world. The Egyptians knew this. They built their civilization on mathematical foundations. We can learn from their example. We can appreciate that mathematical thinking is valuable, not because some curriculum says we need to learn it, but because it genuinely enhances human capability, and has done so for thousands of years. The pyramids will outlast us all. They'll still be standing centuries from now, testaments to Egyptian mathematical prowess, but the mathematical knowledge that created them doesn't have to remain locked in stone. It's available to anyone willing to learn. The methods might look different now, but the fundamental insights that the world can be understood quantitatively, that careful measurement and calculation enable achievement, that mathematical thinking is powerful, these insights are timeless. They were true in ancient Egypt. They're true today. They'll be true for as long as humans are trying to understand and improve the world. So here's my challenge to you. Next time you encounter mathematics, whether in school, at work, or in daily life, remember the Egyptian scribes. Remember that you're not just manipulating abstract symbols. You're engaging with a way of thinking that has enabled some of humanity's greatest achievements. You're part of a tradition that stretches back thousands of years and will continue far into the future. The specific problem you're solving might seem mundane, but the underlying capability you're exercising, mathematical reasoning, is profound and powerful. Honor that capability. Develop it. Use it well. The ancient Egyptians would expect no less from us. And when you see images of the pyramids, or if you're lucky enough to visit them in person, remember that you're not just looking at impressive piles of stone, you're looking at mathematics made manifest. You're looking at proof that human intelligence, armed with mathematical knowledge and applied with skill and determination, can achieve things that inspire awe thousands of years later. That's the shocking secret of Egyptian mathematics. It was and remains testimony to the power of the mathematical human mind, and that power is yours to claim and use. The Egyptians showed us the way. Now we must walk our own path, carrying forward the torch of mathematical knowledge that they helped light so many thousands of years ago. Thank you for joining me on this journey through the shocking secrets of ancient Egyptian mathematics. I hope you've gained not just knowledge about historical mathematical techniques, but also appreciation for the sophistication of ancient peoples, understanding of how mathematical traditions develop and transmit across time and cultures, and inspiration to engage more deeply with mathematical thinking in your own life. The Egyptians were remarkable mathematicians and engineers. Their achievements deserve recognition and respect. But more than that, they deserve emulation. We should aspire to their level of systematic thinking, their commitment to precision and accuracy, their willingness to invest in knowledge and education, their ambition to achieve difficult things through careful planning and execution. The mathematical legacy of ancient Egypt is not just historical curiosity, it's living inheritance that continues to influence how we think and what we can achieve. Every time an engineer uses geometric principles to design a structure, every time an astronomer tracks celestial phenomena, every time a project manager plans a complex undertaking, echoes of Egyptian mathematical thinking resonate through their work. We are all inheritors of Egyptian mathematical wisdom, whether we realize it or not. The foundation they helped build supports everything we do in mathematics, science, engineering, and technology today. As we close, let me leave you with one final thought. The ancient Egyptian civilization eventually faded. The knowledge of how to read hieroglyphs was lost for over 1,000 years, until the Rosetta Stone allowed their decipherment in the early 1800s. Mathematical papyri lay forgotten in tombs and ruins for millennia. The great tradition of Egyptian mathematics fell silent, but the mathematical truths the Egyptians worked with didn't fade. The geometric relationships, the arithmetic patterns, the astronomical cycles all remained, waiting for new generations to rediscover them. And when modern scholars finally deciphered the papyri and studied Egyptian achievements, they found not primitive fumbling but sophisticated mathematics. This tells us something important. Mathematical truth is robust and enduring, but mathematical knowledge is fragile and must be actively preserved. Civilizations rise and fall, languages are forgotten, technologies become obsolete, but mathematical relationships remain true. The challenge for each generation is to maintain knowledge of these truths and pass it on to the next generation. The Egyptians succeeded at this for 3,000 years, an impressive run. We've been doing it in our modern form for just a few centuries. We have much to learn from their success and much to fear from their eventual decline. Knowledge is precious. We must treasure it, maintain it, and use it wisely. The shocking secrets of ancient Egyptian mathematics turn out to be not so much specific techniques, Though those are fascinating but broader lessons about human capability, the nature of mathematical knowledge, the importance of education and knowledge transmission, and the power of systematic thinking applied consistently over long periods. The Egyptians showed us that civilization rests on knowledge, that ambition combined with mathematical planning can achieve the seemingly impossible, that investing in education pays dividends for centuries, and that human intelligence is our greatest resource and most powerful tool. These lessons are perhaps more relevant today than ever. We face challenges the Egyptians never imagined: climate change, nuclear proliferation, artificial intelligence, pandemics, resource depletion. But the fundamental approach the Egyptians exemplified, using mathematical and scientific knowledge to understand problems and develop solutions, remains our best hope. We need to observe carefully, measure precisely, calculate accurately, plan systematically, and execute skillfully. We need to invest in education and knowledge preservation. We need to value expertise and listen to those who have spent years developing deep understanding. We need to think long-term, planning not just for our own lifetimes but for the welfare of future generations. The Egyptians did all of this. We must do it too. So as we conclude this exploration of ancient Egyptian mathematics, I hope you feel a sense of connection across time to those ancient scribes and engineers. They were people like us, with the same fundamental cognitive capabilities, facing challenges in their world just as we face challenges in ours. They developed mathematical knowledge to address those challenges. That knowledge, transmitted across millennia through various channels, eventually reached us. We benefit from their insights and achievements. And now we have the opportunity, indeed the obligation, to add our own contributions to the great stream of mathematical knowledge that flows through human history. What will future generations say about our mathematical achievements? What monuments, literal or figurative, will we leave them? What insights will we contribute to the ongoing human project of understanding and improving the world through mathematical thinking? These are the questions the Egyptian example poses to us. These are the challenges their achievements present us with. The pyramids stand in silent testimony to what's possible. The Papyrus reveal sophisticated thinking from thousands of years ago. Together they tell us that human beings are capable of remarkable things when we apply our mathematical minds systematically and ambitiously. This is the shocking secret of ancient Egyptian mathematics. It reveals our own potential if only we choose to embrace it and use it as wisely as the Egyptians did so many thousands of years ago. Thank you for exploring this fascinating topic with me. Now go forth and think mathematically. The sleepy computer scientist is signing off, but the mathematical adventure continues with every calculation you perform and every problem you solve. Keep exploring, keep learning, and never stop appreciating the power and beauty of mathematical thinking.